All right, so last talk for today. Last but not least is Luigi Alfonsi, and he'll talk about derived n-plectic geometry.
Okay, thank you very much. And of course, I wanted to thank you, Hisham and Urs, for the very kind invitation. I mean, this seminar, this workshop set the bar extremely high. And so I'm going to talk to you about things I've been thinking about in the last months, fundamentally, and this is going to be based on work together with Charles Young, and it is hopefully to appear soon. So if you have very relevant feedback, still in time. So I'm going to talk to you about derived n-plectic geometry. I will tell you soon what I mean for that. Also, the subtitle includes non-perturbative BV-BFV quantization, or at least towards that. I'm not really going to go already into the specific aspect. But you know, it could sound like an oxymoron almost, because non-perturbative and BV quantization in the same sentence is not particularly clear how they could fit together. So I tried to work a bit in this direction. So let me just start with an introduction. So this very, very fundamental idea about what BV theory is supposed to be. So fundamentally, we know that the space of solutions of the field equations of a classical field theory is precisely the critical locus of its action functional. So that's precisely the space of solutions. So the fundamental idea of BV theory is to consider not the critical locus itself, but rather a derived enhancement of that. So something derived, which we're going to see what I mean by that, such that when you consider its underived truncation, you obtain back the ordinary critical locus. So this is very vague for now, because I want to give first the fundamental idea of that. So there have been a few very closely related, really, approaches to deal with classical but also quantum BV theory. Today, I'm going to focus mostly with the classical aspect, because the quantum one will require some extra steps to take. And probably the most frequently used is the NQP manifold approach. So where the algebra of observables is fundamentally given by the Poisson-Digital algebra of functions on an NQP manifold. Then, as we have seen already, even during these days, that's not all of it, because this Poisson-Digital algebra of function gives rise indeed to an L-infinity algebra of observables, considering that this NQP manifold with a -1 shifted symplectic form are secretly, if you want, symplectic L-infinity algebroids, and there is a very nice theory behind that. But it's not the only approach that has been used in the literature, because we also have something that is in the spirit quite similar. So it's the factorization algebras approach, which was is slightly different in the sense that instead of considering a symplectic or a -1 shifted symplectic L-infinity algebroid, they consider a formal moduli problem, which is fundamentally, I'm going to go back on that in a minute, but fundamentally it is a derived stack on this site of Artinian DG algebras, which have a precise geometric meaning that I'm going to mention. And this is often also sheaved on space-time, in the sense that you consider a stack on DG-Artinian algebra, but also at the same time an object that is sheaved on space-time. So this is equipped with a pi-naught algebra of functions and a -1 shifted symplectic form. It's very, like, there is an immediate, if you want, similarity, even if they're not exactly the same thing, with the L-infinity symplectic algebroid, because formal moduli problems are understood to be always equivalent to the Maurer-Cartan functor of a local L-infinity algebra, which fundamentally is a sheaf of L-infinity algebras on a manifold. Then there is also an apparently, it's not moving. Sorry? Oh, pi-naught, well, it's fundamentally a -1 shifted Poisson structure, which is usually called pi-naught algebra, at least in this context. But it can be thought as that, really, as -1 shifted Poisson bracket. There is also perturbative algebraic quantum field theory, which, interestingly, it looks much more different on the nose, but it has been developing things that are extremely related to BV theory from a very different perspective. And as far as the process 1 and 2 already look quite close, there is also research work that connects the second and the third in some, at least in some specific cases. So they are understood to be related. For now, I will mostly focus on the second one, but by keeping on the back of my mind that they are actually very close and related. So what a formal moduli problem is, fundamentally, as I mentioned, is an algebraic derived stack on Artinian DG algebras. So you can think it as modeled by a functor that goes from DG Artinian algebras to simplicial sets that must satisfy some properties. And I wrote here that an Artinian DG algebra secretly is fundamentally can be thought as the algebra of functions on a derived thickened point, in a sense, because Artinian DG algebras are negatively or at least non-positively graded DG algebras, such that the zeroth cohomology is an Artinian algebra, which means that if you quotient out the maximal differential ideal, you just get the base field. So in our case, it would be R. But something that you see in I shouldn't look down. Something that you see in the literature of formal moduli problem and algebraic derived geometry is that a formal moduli problem, usually in that context, emerges as the formal completion of something bigger, which is a -1 symplectic derived stack. In most of cases in the literature, we're speaking of algebraic stacks at some given point. So this is not surprising, because the picture behind it is more or less this cartoon, in the sense that when we do quantum field theory, we are interested at perturbative theory around a fixed solution of the equation of motions, which in the 90% of cases is just the trivial one as far as it is a solution. And what the formal moduli problem are encoding is that you are fundamentally considering an infinitesimal neighborhood of this solution. And what in this cartoon a fully fledged derived stack would be is this bigger thing that you can imagine to formal complete at a given solution. So BV theory, especially in this context, is really hardwired to speak about perturbative physics. So that's just what it does. But I've been in the past, for several reasons, including dualities in string theory and so on, very interested in global aspects of string theory and of quantum field theories in general. So I guess that we have, this is very morally speaking, yet still, we have that a formal moduli problem is very, very related to perturbative physics. It's hardwired to describe that. That's what it does. It does it well, and that is the how it was constructed. On the other hand, this hypothetical, if you want, at this stage, formal derived smooth stack would be more suited to describe potentially non-perturbative physics, if you accept the fact that you need to look at derived, so in some sense graded objects, to speak about quantization and so on. So as a very simple comparison, it doesn't make so much sense to compare them like that, but just to have a flavor. What I have on the left, which is an L-infinity algebroid that is supposed to encode, well, the data of really of a trivial gauge field, is very different from what I have on the right side, which is fundamentally this mapping stack between some manifold your spacetime, for example, and the moduli stack of G-bundles with connection. So they are clearly two different objects. This one on the right side knows about the global topology underlying each of these bundles and so on. Then, of course, we have seen today in the talks that preceded me that you can also imagine of replacing this moduli stack with something extremely much complex, and this argument would apply still. So it is undoubted that the right side knows about the global geometry and so on, the left side no, as a simple example. And so M theory, but also string theory, is known to include higher gauge theories, or even just gauge theories. So we know that quantization of gauge theories is not really yet a simple matter, and it probably requires BV theory. So we are accepting that, or at least we are suspecting that we need to look at derived geometry. On the other hand, we also know that finite gauge transformation and global properties of gauge field, including the magnetic charges, the Aharonov-Bohm phase, and so on, of gauge field require higher geometry, and possibly possibly in a global sense. Moreover, I said here we have global string and M theory dualities and other non-perturbative effects that I don't precisely know. And it's not too strange to think that to deal with the quantum properties of string and M dualities, maybe it's necessary to have, in some sense, a derived geometry that encodes also this finite higher gauge transformation. So that's a legitimate expectation. I don't know if that's right, but surely BV theory, as it is, has something to say about string and M dualities. So that's something that one could expect. Now, I also added it's not totally clear how the zero-symplectic BFV structure that you often have at the boundary would fit in this derived geometric picture of the formal moduli problem. Maybe there has been more research in the NQP manifold approach to BV theory. That's probably more clarified there, but if you want to pick precisely the formal moduli problem, factorization algebras approach, that's not very clear. I don't think has been addressed too much. Okay, so these are motivations why it could be legitimate to try to consider these kind of objects. And then another, if you want, different motivation, which gives also the name to the main title of the talk, is that so we know that n-plectic geometry, or as it was probably previously called the higher symplectic geometry, fits in this following picture, at least in some cases, right? So we can consider an n-plectic structure, so fundamentally a closed non-degenerate n+1 form, and we know that that should give rise to, can be pre-quantized by giving rise to an n-1 bundle gerb, and in some realistic situations, especially the one that emerge from field theories, there is it's often possible to consider transgression of the upstairs and downstairs and get a symplectic structure which gives rise to pre-quantum U1 bundle. So a very classic example is the one of the bundle gerb on a smooth manifold, which can be transgressed to a U1 bundle on the loop space of such manifold. And that's interesting because it's connected very closely to the geometry of a closed string, right? So that's fundamentally by doing some more steps, this transgression here is really connecting, if you want, the ordinary quantization of the phase space, which is infinite dimensional, of a closed string with an n-plectic structure on somewhere else. Now I will not be very specific. And also there are, as an extra motivations, there are some interesting connections between Courant's and Vinogradov algebroid with things that come from symplectic and potentially n-plectic structures. So now this is possibly deep down that's related to the fact that the Vinogradov and Courant algebroid in the case for n equal 2 say something about the symmetries of a pre-quantum bundle n-1 gerb, or at least is probably related to that, but nonetheless that creates an interesting connection between all these things. So a question, if you want, a second question can be, can this picture or something of this picture be in some sense translated also in the derived sense? You know, like here we have, on the left side we have symplectic structure and pre-quantum U1 bundle, but then in the derived geometric literature there is a notion of derived symplectic structure. And I will mention at the very end that there is also some attempt of constructing pre-quantum or quantum U1 bundle in that setting, and they have some interest in themselves. So fundamentally, this second question is there a right side also for what concerns derived geometry? So that's more or less the starting point, and I will be telling you something about formal derived smooth stacks, which I tried to give my time in this last month. Let's see. So I will be using this perspective, which could or could not be familiar, where fundamentally you want to encode a geometric space as a functor. So you could call it a functorial geometric perspective. So in this simplest class of examples, if you want, so this is just a cartoon to convey an idea, if you want. So an ordinary geometric space can be encoded by its functor of points. That's well known even from algebraic geometry. So you want to consider you want to construct a space by fundamentally constructing a sheaf on a category of probing spaces, which if you ask to an algebraic geometers, they could be affine schemes, for example, or the opposite category of R algebras in the real case. And on the right-hand side, you would have sets. So fundamentally, to describe a geometric space, you need to know the sets of ways how you can probe such a geometric space with your test spaces. So and that can be called the functor of points. But then there exists indeed a generalization of this perspective, a categorification, where you fundamentally categorify your right-hand side. Instead of sets, you consider infinity groupoids, which you can think indeed as a particular class of simplicial sets that satisfy a condition called the Kahn condition. And you keep unvaried your toolbox of probing spaces, so they can still be affine spaces or smooth manifolds, something easy to treat. And in this case, you can encode something that could very informally be called a higher geometric space, or if you want, a stack. So now, once you're arrived here, the next potentially natural thing to do is to categorify the left-hand side too, right? So you could do that or try to do that. And what is called in this case is usually a derived stack, or if you want, with a more geometric, informal terminology, you could call it a higher derived geometric space. So you will want to construct a functor between now a quasi-category, if you want, of derived probing spaces to infinity groupoids, which must satisfy some conditions which I don't want to enter to not be too technical. So fundamentally, this is just a strategy for defining objects that are going to be seen in a moment. So now, the very first step is to consider as probing spaces smooth manifolds. This is done often, and if you consider sheaves on them, you may call these sheaves smooth sets as a but you can also consider stacks on smooth manifolds, and they will be smooth stacks indeed. So now, this was just the starting point of that generalization. You can add an extra step and consider formal smooth manifolds. So you are just replacing smooth manifolds with manifolds that are allowed to be infinitesimally thickened, and just call just call these sheaves and stacks to sets and infinity groupoids, form smooth sets or form smooth stacks. And they will have a precise geometrical meaning in the sense that now you are allowed to consider objects that you can probe, not just with manifolds, but also with these infinitesimal thickened manifolds or points. Now, what I tried to consider in what's going to follow is fundamentally the last step of the square, if you want. So as I mentioned in the previous slide, at the third point, you can try to categorify also the left-hand side. So in this case, you can try to categorify formal smooth manifolds. And this has been done in the literature. There is a fairly recent, or maybe there is more than one, but there has been a very compelling recent formulation of formal derived smooth manifolds. And derived stacks on this site here could be called formal derived smooth stacks. So they would be formal in the sense that you can go, if you want, there is a notion of being infinitesimal in an ordinary sense, but there is also a notion of being categorified in that unusual way on the left-hand side. So what are formal derived smooth manifolds? So fundamentally, the way that has been usually used, so for example, by Spivak, Carcedi, and so on, has been to define first homotopy infinity algebras. So first, infinity algebras are essentially the smooth algebras we know. So the algebras on, for example, differentiable manifolds. So to define homotopy infinity algebra, you need first to consider simplicial infinity algebras, and they can be equipped with a certain model structure, which I will not give detail, and that model simplicial category, when you consider just a fibrant cofibrant object, you can call that homotopy infinity algebras. You will have a well-defined quasi-category of that. So how do formal derived smooth manifold comes into play? So there is this nice, so this is not the definition of formal derived manifolds that is used in the paper I'm referencing here by Carcedi Stephens. They use a much more, if you want, abstract and beautiful definition, but for all the effects that are needed in this construction, I will effectively use this equivalence in the center as a definition for simplicity. So fundamentally, if you want, by definition, we can call derived formal manifolds the opposite infinity one category of the infinity one category of homotopically finite represented homotopy infinity algebra, where homotopically finite represented fundamentally means that if you consider the homotopy of the homotopy groups of these objects, they need to be finitely presented in the ordinary sense. So roughly, that's what they need to satisfy. So if you want an intuitive picture, you're fundamentally defining a derived formal manifold U as a geometric object that by definition must have an algebra of smooth function that looks like this. So fundamentally a simplicial infinity algebra. So they are dually defined this way. So now so there is a machinery to define derived stack once you have a quasi-category with certain properties. So it's possible, I believe, to define at all maps of these formal derived smooth manifolds because you fundamentally have the notion of local diffeomorphisms on ordinary manifolds. So you can really use the usual definition of et al maps, considering that the zero, the underived truncations of these formal smooth manifolds must be a local diffeomorphism together with other conditions that it's not important to mention now. So by using these et al. Mops, you can make this quasi-category into a fully fledged infinity one site, and by Toyn Vezzosi, there is a machinery that provided that it makes sense to define this infinity one category of formal derived stacks. So there is there is a machinery that tells you that there is a good sense in which there is a model structure that can be used for this work. But this is very general. Actually, for physical reasons, what we wanted to look at first is much more of a toy example than that. And then, so what we tried to do is to define a notion of formal derived smooth set, which, if you take it literally as expecting a map to sets, that doesn't make much sense. So we did something much more simple, if you want, than that, in the sense that we just called the derived formal smooth sets all the derived formal smooth stacks, such that they are their truncation is a formal smooth set. So it's really just that. And fundamentally, you get these relations of embeddings between these just defined category of derived formal smooth sets, of derived formal smooth stack, of formal smooth sets, the ordinary ones, and derived formal smooth set. I think I put twice the same thing. So this should have been without the D here, so there would have been just formal smooth stacks. So a very commonly used example that would be much more concrete is going to be an affine derived formal smooth set. So there is a way why, given an homotopy infinity algebra, you can automatically define a derived formal smooth set such that the algebra of functions on it is going to be precisely R. And funnily enough, for what concerns smooth geometry, that's really wide classes of examples, in the sense that if you consider algebraic geometry, you will have that affine spaces are a very special class, but in smooth geometry, for example, all the formal derived smooth manifolds belong to this class. And so this maps starting from affine derived formal smooth sets, which are written with this symbol. When you consider the underived truncation, you will just obtain an affine C-infinity scheme that is the spec of pi naught of your original algebra R. So R it was fundamentally a simplicial infinity algebra. What you get here is just a infinity algebra. And the embedding of the ordinary thing into the derived thing works pretty much the same. So in this case, R is to be considered ordinary. It can be immediately embedded into the derived thing. So what can be said now about this? Okay, so there is this. So this is something nice, which I fundamentally just recognize in the algebraic, the derived geometric papers, and fundamentally recasted by replacing commutative algebras with infinity algebras, and formally is very similar. So there was a nice recognition, because So fundamentally, you can consider these categories of reduced infinity algebras, so where you exclude every infinity algebra with non-zero nilpotent elements. So they are fundamentally these infinity algebras of differentiable manifolds. So there is a reduction functor that's given a homotopy infinity algebra fed an R. It gives you back a reduced algebra, which is just the pi naught of that simplicial algebra, and you quotient out the nilpotent, the ideal of nilpotence element of pi naught. So now this functor fits into this adjunction, which then, given an adjunction of this fundamentally, so secretly, this is the opposite category of this formal derived smooth manifolds, and this is the opposite category of just ordinary smooth manifolds. You will have automatically seeing that they induce these quadruplets of adjoint functors between what I call the derived formal smooth stacks and what I call the smooth stacks. And smooth stacks is just stacks on ordinary manifolds. So, but this quadruplet, I fundamentally seen it before. And then, so there exists, I want to stress that there exists precisely an algebraic version of this. You just need to replace the infinity algebras with commutative algebras fundamentally. And so this can be recognized as a differential cohesive structure as defined by Hurst. Where fundamentally you have this relation between derived formal smooth stacks and ordinary smooth stacks. And in some sense, I think this is just, if you want, a little generalization of what has been already considered, where you just add this derived component, if you want. This quadruplet of functors, instead of telling you just how to embed or contract away the formal thickening, it also tells you how to contract away the derived formal thickening. And you have, so how do this functor look like a little bit more concretely? Well, if you consider an affine spec of some reduced infinity algebra, you just embedded it into the derived thing. And if you consider one derived affine thing, you will fundamentally just send it to the spec of the reduced one. So for example, if here you have a formal smooth derived manifold, this functor will send it just to the ordinary smooth manifold where all the formal derived component has been contracted away. And so since I fundamentally just looked at it and recognized it, it can also, as a differential cohesive structure, then we can use the tool that has been defined there already for fundamentally by generalizing what has been already written for formal smooth stacks to derived formal smooth stacks. And very, very morally speaking, thanks to this differential cohesion, we can fundamentally do differential geometry in a way that makes sense. And so it is possible to slightly generalize the results of Kavkin and Schreiber. I'm probably doing a bit slowly with time, but fundamentally it's possible to consider in a way that makes sense derived infinitesimal disks and also more important, because of this, there is also possible to make sense in a very general sense of the notion of jet bundle by considering fundamentally the fiber of a jet bundle in this very general context is required to be equivalent to the formal smooth stack of sections of your bundle that you're considering on this thickened disk. So now, and I also, so I think there is this nice picture which still is just it's fundamentally a straightforward generalization from the work of Hauer-Ost, where instead of a formal smooth stack that is generalized to a derived formal smooth stack. But there is this nice picture which I think is relevant for physical reasons, which we saw at the very beginning. So fundamentally, you get that derived formal smooth stack fit in this little sequence where you can embed you can embed just ordinary smooth stack. That's as we have seen a few slides ago. But then you can also fundamentally restrict whenever you want derived formal smooth stacks on just this formal derived manifold to just formal derived infinitesimal disks, because they belong to that category, they are there. So you can restrict and what you get is essentially a formal moduli problem because the homotopy smooth algebras of functions on this infinitesimal disk are fundamentally DG Artinian algebras. So in some sense, this should give an indication that in this category you have a formal moduli problem, but also more extended things. So now there is already a machinery, as I said, in algebraic derived geometry that tells you how to define a certain amount of things. So what I've been trying to do for some time is fundamentally to translate that from algebraic geometry to smooth geometry, fundamentally by trying to replace commutative algebras with C-infinity algebras. So the algebra of, so the differential forms get a generalization fundamentally, and you will obtain something, probably need to run a little bit more. You will have something which has a fundamentally a B degree, because you will have an internal differential Q that comes from the fact that the smooth functions on X are it's not just a C-infinity algebra, but it's going to be something simplisher, which will give rise to a vertical, if you want, differential Q. But you also have the RAM differential that goes in the direction of increasing the degree of the differential forms in this sense. So there is more structure in this direction, in a sense. And how does the definition of closed differential forms changes in this context? Well, so fundamentally, you need to consider here between parentheses what is usually called the RAM algebra, and shift it by P, where P is the degree of the form that you are considering. And you will obtain fundamentally this complex of n-shift closed P form, and a closed form is going to be defined not just as an element, but it's going to be defined as an n-cocycle in this complex. So fundamentally, you are as I write here, by selecting an element, you are selecting a formal sum of this form, where each omega I is an I form, but is going to have this degree increasingly shifted. And then we have to satisfy the potentially infinite number of equations here. So fundamentally, this amounts roughly to the fact that the Derived differential of this omega p is not 0 on the nose, but is 0 up to a homotopy, which is going to be itself closed up to homotopy and so on. Of course, this can be truncated, even truncated immediately at omega p, as it often happens, but it potentially can just keep going. More compactly, this can be expressed all together in this equation here, where omega is the this infinite sum. And so I don't think I have a lot of time, because I wanted to give a little show of ordinary n-plectic geometry, but probably I will have to run a little bit more. So, okay, what is interesting to me is that in n-plectic geometry, there is going to be a bicomplex in a completely different sense, because the Derived differential on a jet band fundamentally can split between horizontal and vertical, and you will have a B degree given by the fact that your differential form can have a certain degree on the base manifold fundamentally, and a certain degree in the directions of the fiber. So this was interesting, because I will put later these things together if I will have the time. Another step again. So okay, here I'm still recollecting some facts about Lagrangians. So it is well known, as since Anderson 1989, that the Derived differential of a Lagrangian density can be decomposed in two forms. The first one is going to be called the Euler-Lagrange form, where m,1 form means the degree in horizontal, vertical, in the sense I just described, minus the horizontal derivative of something, of a theta, that has a different degree, m-1,1. So now the vertical differential of this theta is called presymplectic current. So this is automatically defined for a classical field theory, and one has, so it's called presymplectic because for certain reasons it looks like it has to do with symplectic structure given by the classical field theory, but hopefully I will reach that. But for the moment, if you take the Derived differential of it, it's surely non-zero, and it's actually given by the vertical differential of the Euler-Lagrange form. So let's see how much. Okay, so this is something that appears in the paper I mentioned before too, by Kavkin and Schreiber in 17, where in a more general setting about PDAs is defined a certain concept where this is a particular example, and for now we just rebranded Euler-Lagrange critical locus, and is fundamentally the subspace of the jet band where the equations of motions are imposed at each derivative of the jet band. So as you can see in this final equivalence, if you consider the critical locus of an action functional on an infinitesimal disk, so fundamentally you're considering germs of solutions, what you get on the left-hand side is the is this Euler-Lagrange critical locus at x. So it is this 5. And so now we just say that so if you put fundamentally your classical field theory on shell in this jet bundle sense by pulling back the pre-symplectic form on this space where the questions of motions are imposed on all the germs, you will get an example of an n-plectic forms on this space. So now, well, I will have to go a bit faster on that. So fundamentally, what I try to start from is in analogy with the derived symplectic structure, is to consider a derived version of an n-plectic form, which is fundamentally going to be still a closed, as defined earlier, form. So notice that closed means that there is that potential infinite tower of shifted, increasingly shifted form, such that it obeys a non-degeneracy condition that is reasonable. And a derived symplectic structure will be in particular an example of these derived n-plectic structures. So now, to make contact with classical field theory, we notice that it's possible with just a few steps to recast what we called Euler-Lagrange critical locus as a zero locus of a section, which is fundamentally the lift of, well, I don't have time to describe it precisely, but something given by the Euler-Lagrange form. So morally speaking, this is going to be the Euler-Lagrange form and all its derivatives in the horizontal directions. So it's possible to write this subspace of the jet bundle as a zero locus of this section. But then now there is a machinery for considering the derived zero locus of a section on something. So what one can do is just really look at this alternative, if you want, definition of Euler-Lagrange critical locus and make it derived, in the sense that you can embed the three spaces on these vertices inside the category of derived formal smooth stacks, and form it take the limit there. And then there is a well-known machinery that allows you to do that in case you know what is the section of the bundle that you want to put to zero. And as a DG algebra, fundamentally you get that the algebra smooth functions on this thing must be of this peculiar form. So they're going to be sections on the jet bundle, but not of vectors on, they're not going to be polyvectors on the jet bundle, but something closed. So now by looking in coordinates at the indices, they do make sense, even if they look a bit strange, because this is supposed to be the dual of the jet bundle, so the cojet bundle of the dual of the vertical tangent bundle of your starting bundle. So it sounds strange, but by writing it down in coordinates is really makes sense, the position of the indices, if they're up or down. And then it's going to have a differential given by just contracting these things with your germs of the Euler-Lagrange form. So now the nice thing is that since everything is derived, now you can consider derived differential forms in the previous sense, and you have that everything is tree graded, in the sense that there is going to be a first number that tells you what is the degree in the horizontal direction of, so fundamentally on the base manifold, on the vertical direction, so in the fiber of the jet component, if you want, and also a degree of how, in the BV sense, if you want. But then now, since you have this picture, you can ask, but then now, what about the closed forms, which were already quite more complicated than the ordinary versions? Well, so if you try to make a reasonable definition, considering what we saw before of what a closed PQ form, so by picking a starting degree in the horizontal and vertical degree in the jet sense, you will write something like this shortly. And the nice thing is that instead of having an infinite, if you want a potentially infinite array of these forms, you will have, well, more, because you can start by a PQ form with a BV degree n, and well, there should be a -1 here, but you can keep decreasing that degree, and still you have a choice on what to increase if the horizontal or vertical one. Yeah, of course, when you go too high with the horizontal degree, is going to truncate in that direction, but the rest can potentially keep going. So now an element is going to be given by this very infinite tower of things, but how does the to be a cocycle, so to actually be a closed form, what equations does it have to satisfy? So you have these lots of equations, so this increasingly big set of equations for every degree, and that's what it looks like, and it's going to be actually relevant for physics, at least in a quite baby example, because we considered only really what I called earlier derived smooth set. But first there is another thing that needs to be introduced before getting to proper physics, which is the transgression of the forms we just seen. So it's not obvious on the nose at all that it should be possible to transgress more or less like in n-plectic geometry in the ordinary sense to in the derived setting. So fundamentally, what saves us is that it still holds this property. So in some sense, what I called the derived Euler-Lagrange critical locus of a Lagrangian is still given at each fiber by gems of the derived critical locus. So this holds still in a derived sense, which is good, because then fundamentally it tells us that we can transgress things. So not too surprisingly, there is a transgression of just bare forms where, so fundamentally of this form, so which generalizes the one on the non-derived critical locus. So fundamentally you can take a dimension m, so in full dimensions on the horizontal degree, q in some q in the vertical direction, and you can obtain something that is just a q form on the derived critical locus, so this derived space of solutions, and they keep the same degree shift, so if you want. And so it's not very surprising that you can specify this thing for closed forms. So if you just take the equations of the cocycle I showed you earlier, and you look at each of them and see what they transgress to, you still get something that satisfy, crucially, the equations to be just a closed Q form on this side. So that works. But then the fact that it's derived, and indeed you have this infinite array of things, allows you also to do more things. Because so if the boundary of the manifold that you were considering is trivial, so it's just 0, and you consider a P that is less than M, where M was the dimension of the manifold, then you can, in some sense, transgress things in the wrong dimension, in the sense that, I said that you have this increasingly shifted array of differential forms. But then if you consider a submanifold of your spacetime in the wrong dimension, you're still going to hit something differently from the ordinary case. And therefore you get something that obtains a degree shift on this submanifold that you have chosen. So that's something you don't observe in ordinary things. And if the boundary is non-trivial, there's just a boundary, you get even more, because fundamentally you can transgress your starting derived closed form both on M and on its boundary. And you will see that what you obtain on the right-hand side, so on the derived critical locus, the big one, the infinite dimensional one, is given by these equations, where the little omega will be the transgression to M, and this one is going to be the transgression of the boundary. So you get something that fails by this amount to be closed in M, and something that is closed on the boundary. And crucially, the thing that you get on the boundary has a degree shift of +1. So you get something that is automatically degree shifted in +1. So for example, if you start with something that was degree shifted, so if you set things so that this was shifted -1, this one is going to be shifted 0. That motivates this bit naive notation of BFV. So now this was the properties just of closed forms. So now to make a very, very quick contact with physics before there's no time anymore, if there is time really. So fundamentally, by using a notation that slightly improper, because this is really a toy example of what BV and BFV theory will have to be. For that we need more than formal derived smooth sets only, so just to make that disclaimer. But you can, so earlier I said in the ordinary case, if you pull back this thing to the critical locus, it becomes just n-plectic. In the ordinary sense. Here is not true. Like if you pull it back to this derived Euler Lagrange critical locus, it's not going to be just n-plectic on the nose. On the other hand, you have also canonical -1 shifted M2 form. And what does happen? It happens that so in other terms, so not in derived geometric terms, this was sort of secretly known in the literature, but the interesting thing is that this formal sum can be recasted in a closed form in the derived geometric sense. So fundamentally, if we take that presymplectic form that I spoke about earlier on the jet boundary, you pull it back on this derived or Lagrange critical locus, you will have that is not n-plectic, but so it's not closed under the Derived differential, but it's closed under the Derived differential up to an homotopy given by this other -1 shifted thing, and which is itself closed under the Derived differential. So this is an example of the very long set of equations that I showed earlier in the very general case, but in this case it gets truncated almost immediately, but it is long enough to encode something non-completely trivial. So then if you plug in the map I showed you earlier, you can get a transgression of this form where you take this little formal sum and you can transgress it on something that lives at the same time on M and on the potential boundary of the so on the boundary of the space-time you are considering. So you get derived differential forms on the derived critical locus side, the infinite dimensional big one, that look like this. So this is almost wait, there is well, this should have been a BFV. There is a missing F, but you get that this is so this right, yes. So you get that this is almost closed in the derived geometric sense up to this term that comes from the boundary, and crucially, the term will have a different degree, so what you would expect in physics. So now, that's not definitely not time. So I guess just a little outlook before I finish. So I wanted just to say that this could be, I mean, this was really a toy example in the big picture at the end, but it seems potentially a good setting to go beyond BV quantization as is intended now, because we know that there is research in a higher geometric pre-quantization that involves surely pre-quantum bundle and gerbs and potentially n-plectic structure, at least in some cases. And we know in derived algebraic geometry there is a notion of geometric quantization that makes use of this derived differential forms in this derived closed differential forms and so on. So maybe that's possible to go to say something beyond the perturbation version of that. And then potentially that opens the door, if you accept that, to go beyond the BV-BFV theory, in the sense that instead of considering forms valued in G, you could consider this mapping stack of G bundles on X and try to consider the derived critical locus of something like this. So not anymore this toy example where everything is not really BRST, but really something that is higher in a very truthful sense. So is it possible to go a little bit beyond that? And it would be nice to investigate some aspects of global aspects of dualities, I think. Thank you for your attention. I'm sorry if I went over time. Oh dear, yes I did. Thank you very much.
So there are questions?
Oh, yeah.
A very basic question. There exists multisymplectic geometry.
Yes.
Do you can you do the same for what you did? I mean, higher multisymplectic geometry.
When so in a sense,
what would be the use? I mean,
yeah. So I've been extremely vague between the distinction between ordinary n-plectic geometry and multisymplectic geometry, because usually they mean slightly different things, in the sense that in some sense n-plectic geometry is more general because you just ask a space where you have a closed non-degenerate n+1 form, and that's it. But I think that one could intend like multisymplectic geometry, I think in the sense you mean as an example, like where you are provided input from classical field theory. So I would like.
It's very basic. When you are the volume in an n-dimensional space, the volume form is the symplectic form of an n-1 plectic geometry.
Okay.
It's very.
Okay, no, you're right. I understand now. Like, if you want, if you have, the classic tree form on a. Yeah, I see.
I guess that also, on G2 acting in 7 dimensions has a two-plectic structure, because there is an invariant tree form, and so on.
So I think that so this was built or tried to be built in analogy with the derived critical locus that appears in BV theory. So in the sense that so in BV theory you consider the shifted cotangent bundle and so on, and that's fundamentally the derived critical locus. And the fact is that I don't really consider generic spaces where you have your derived or not n-plectic form. So for example, if you tell me, it's always if you want the shifted cotangent bundle of something, what that's what I mean. It's never if you tell me like an n-sphere, well, that's not among the examples. I guess you cannot really feed that to this thing. You need the derived critical locus of something, I guess.
Yeah, but I mean the basic symplectic structure that you are making higher, very roughly, is it's an invariant to form or what? Or can be an
Oh,
N
you
form?
mean?
That's the question. Can also be an N form, an invariant N form which is closed, or?
Yes, in the sense that I mean you can. So it's true that I mean you can have it truncated and non-shifted, right? Like zero shifted and truncated, so that there is not an infinite array. There is just one, and this in degree 0. And then if you consider a derived stack that is just the embedding of an ordinary smooth manifold, then I think you would generalize that in the sense, at least I believe the symplectic version, which there is a lot of literature about it, derived symplectic geometry, I think it generalizes ordinary symplectic geometry in the sense that by making a lot of assumptions in the derived case, you reduce to that. So yeah, I think it should happen. I think because you just I think you would have to it should happen. Like it's true. You can consider a closed N form on something that is the embedding of a smooth manifold, and then you have a closed form. Just I think.
Okay.
Okay. Thank you.
Thank you.
Thank you.
Among the many differentials that you were talking about, was there the BV operator?
Oh yeah. So it's fundamentally what I call the Q, but I left a bit of ambiguity because, in a sense, you have Q on the derived critical locus, the proper one, which is supposed to be literally the BV operator. And then I also use the same symbol Q for the internal differential of the other one, the Euler-Lagrange critical locus. And they are related in the sense that if you transgress Q, so the BV operator applied to something, then you get the internal operator of the other one applied to the transgression. So it is mapped one into the other, I think. So that's why I left it with the same symbol fundamentally. But yeah, to be very precise, I should have used two slightly different symbols and make precise that they go one into the other.
Okay, and I have another. Thank you. And I have another question. Maybe I missed something. How does your category of C-infinity algebras know about smooth manifolds?
Oh, so fundamentally, you can embed smooth manifolds, or at least rather. Well, you can embed smooth manifolds into the opposite of C-infinity algebras, in the sense that given any smooth manifold, you can consider the particular C-infinity algebras that is, I mean, the C-infinity algebras, the ordinary ones, are defined fundamentally as a Cauchys, so on Cartesian spaces. So in some sense, if I give you R, you need to write the set of maps from your manifold to R. If I give you R2, you need to map. I need to give you the set of maps from M to R2, which happens to be the square of the first one, really. So you can embed the smooth manifolds into the opposite of C-infinity algebras. You don't really lose information.
Maybe it's a sort of well-known but not widely appreciated theorem. Some people call it Miller's exercise. It turns out, surprisingly maybe, the functor from smooth manifolds to R algebras, which takes a manifold to its ring of smooth functions. That is fully faithful. And which is so it means smooth manifolds are more algebraic than you might think, and I guess that's being used.
Thank you.
Yeah. So this is in Miller-Stashev is an exercise, but it was proven much later, I think. I mean, it's a bit more.
Okay, thank you.
Derived symplectic shift is symplectic. Right.
Yeah, that's a very interesting question where I don't really have an answer, but there was this extra slide which was, I didn't show because there was no time, but it was quite suggestive in the sense that, so this is nothing to do with n-plectic things, just symplectic things. But in ordinary symplectic geometry, you get derived brackets that look like this, where pi2 is the honest Poisson structure. And very intriguingly, in derived, there is a notion of derived Poisson structure that corresponds in a certain way to, a derived symplectic structure gives rise to a derived Poisson structure. And they fundamentally look like this. They are like an infinite sum, again, of increasingly shifted p vectors. And they satisfy this equation, which still can be expressed as an infinite number of equations. And interestingly enough, they do give rise to an L-infinity algebra that is not just derived in a sense, but is also higher in the sense that you have this projection of a lot of things. So that's really this is really work in progress. I wouldn't be able to say much about it, but something that is intriguing me now is to generalize the, moving from here to general symplectical infinity algebroids. That seems interesting because this is in the literature. Is not.
One last question. You mentioned that Safronov has a geometric. Because you have higher forms, should I look there?
Well, he's working with derived symplectic structure, right? So he doesn't have that problem. But yeah, if I keep going with derived n-plectic forms, I will have that problem. So yeah, he doesn't. Oh yeah. Well, it's true in the sense that you have this array of forms. Yeah, that's true, but I think it's not a great issue for him in the sense that I think so you have this, if you want to groupoid of differential, of closed differential forms where the objects are these choices of omega, and then there are homotopies between them, and then in some sense he leaves all of that to the connection of something which is, according to him, a bundle gerb in a sense. So it's interesting because in some sense you get a pre-quantum bundle gerb even if you started for something that was supposed to be symplectic, such as a derived symplectic thing. So yeah, I mean it's it is interesting. I didn't think too much yet about Lagrangians and so on, but they are quite different from the ordinary setting, because in some sense if you have so there is not a thing such as a Lagrangian subspace. You rather have a Lagrangian morphism that needs to satisfy some conditions, but rather, even better than that, it needs to be equipped with an extra structure that makes that condition satisfied up to an homotopy. So they are quite weird objects in comparison to the ordinary ones. So yeah, it is an interesting observation that if you derived quantize even just symplectic structure, you are really feeding it forms that are higher forms too secretly. But I guess they are not, probably is more important what sits in what is the first one, basically. There must be a difference. I think it would be hard. It will be harder for n-plectic forms, and probably we have some of the issues you have with ordinary n-plectic forms. That's very easy to expect. Thank you.
Thank you very much again.
Thanks to you.